Hi, so my name is Rafael Trinidad, and I will be presenting quantum computing for the final presentation for this class. What is quantum computing? So the left image shows what a quantum computer looks like. So quantum computers, they solve problems in a completely different way from the traditional computers we use every day. So classical computers, they interpret information in terms of ones and zeros, which we call bits. Quantum computers instead, they use qubits, which make use of a property called superposition. So with superposition, uh, superposition enables information to be processed in a state that combines both 1 and 0, not just a single state. So a common analogy would be a coin, how not only could it be in a state of heads or tails? The coin can also be in a state of like a flip. So in a coin flip, it's neither in a state of head or tails. So it's kind of a mix of both. And until this qubit is measured, the qubit exists in both states. And quantum entanglement, um, in the context of quantum computing, entanglement is when two or more qubits become linked. And the state of one qubit affects the other no matter what when two qubits are entangled. And this happens, you can create an entanglement using this thing called a quantum circuit, similar to a logic circuit um, when operating on bits. Instead, with a quantum circuit, you're operating on qubits instead. So logic circuits affect the state of bits, and quantum circuits affect the states of qubits. Then on the right, you'll see the like a visualization of bits and qubits. So bits, as I've mentioned before, could be in a state of 0 or 1, and qubits could be best visualized as a vector. So what are quantum computers best used for? They're best used for solving pretty hard problems that are really slow or inefficient for a classical computer to handle. So some common examples are molecule simulation, breaking or improving cryptography, optimization problems, searching large databases, machine learning, and AI. But given these examples, quantum computers aren't going to replace classical computers anytime soon. So those examples I just gave aren't really everyday common tasks most people use. Um, so like a typical task for a classical computer would be like internet browsing, and you don't really need a quantum computer to do that. So I will proceed to show off a demo using the Qiskit open source software development framework, which was developed by IBM, and it allows you to work with quantum computers. And Qiskit provides tools to create and simulate quantum circuits, like I said, are kind of like logic circuits, but for qubits, and run quantum algorithms on simulators or real quantum hardware. The algorithm I'll be demonstrating would be Grover's algorithm, which is best used for unstructured search. And with Qiskit, you can also visualize the results and understand quantum processes. So let's get started with the demo. So a little bit more background about the Grover's algorithm. So what it does, it solves an unstructured search problem, like I mentioned before, but much more efficiently than what classical algorithms are capable of. So with the Grover algorithm, you're able to find a marked item, or in other words, a solution, from an unsorted database of n items. But you can do this in big O of square root of n time compared to the big O of n, the linear search from the classical algorithms. So The steps involve first like the initialization, where you start with the uniform superposition of all possible inputs, and then the oracle step, where you flip the sign of the amplitude of the marked correct solution. Then diffusion, where you reflect all amplitudes around their average. And then fourth step is when you apply the oracle and diffusion operator uh, about square root n times. And step five is the final step, where you measure the states and you arrive to the solution. All right. So now I will go over the Grover algorithm, and this was some of this is covered by the Qiskit tutorials, but let's get started. And so the first code block, this imports some of the necessary tools and libraries to use Qiskit, which is covered by the introductory Qiskit tutorials provided by IBM. And now for the second code block, we want to connect to the IBM Quantum Runtime Service and find whichever quantum device is least busy and available to us. And in this case, it's IBM Brisbane. And as you can see, I ran this notebook beforehand to save some time. And for the next code block, we had to create an Oracle function, which is part of Grover's algorithm. This function, or Oracle, what it does, it marks a target bit string as the solution by applying a phase flip, which is basic. This uses a Z gate and takes as input the marked states. So we create a quantum circuit with the num qubits variable, which is basically the length of all of the marked states. And for each marked state, we go through this next loop to maintain. Oh, yeah. And for the Qiskit ordering, the bit order is reversed. So we had to maintain the ordering of Qiskit. And we find the positions where the target state has a 0 and apply the X gates on those bits. These X gates essentially are like the NOT gates from the logic circuits, but this is the equivalent gates for the qubits. We also add a multi-controlled Z gate to our quantum circuit, which flips the sign or the phase of the quantum state. We then had to undo the X gates that we previously applied. And then this function creates returns the quantum circuit, representing our oracle. The next, we set our marked states. In this case, I want to keep it simple, so I just chose one marked state, and the marked state was 101. So we call the oracle function on our marked state, and we create the quantum circuit, flipping the phase of our marked state. We also create the diagram of our oracle circuit using a matplotlib, and as you can see, here's our diagram. And we create a Grover diffusion operator with our oracle, and this operator combines both the oracle we created and the diffusion operator circuit. We also get to see what the Grover operator looks like when broken down to its most basic quantum gates. So we have another nice diagram here. And what this next code block does is that it computes how many times the Grover operator should be applied to maximize the chances of finding the marked states. And what the Grover operator essentially does is that it amplifies the probability of measuring the marked state. Now, moving on to the next code block, we finally create the quantum circuit that performs the Grover algorithm. A new quantum circuit is initialized, and then we use the same number of qubits as the Grover operator. Then we apply the Hadamard gates to each qubit in the circuit to put all qubits into a superposition of all possible states with equal amplitude. And the Grover operator is then applied, the optimal amount that we calculated from the previous code block. And the Grover operator is also integrated into the quantum circuit. We then attempt to measure all of the qubits in the circuit to collapse superposition. Then here we perform some optimizations on the quantum circuit to make use of the hardware architecture of the quantum backend that we're specifically using. And almost approaching the end here. We use a sampler primitive to execute the quantum circuit and collect measurement results. So we have 10,000 shots or repetitions. So what this means is that we execute the quantum circuit 10,000 times and collect measurement results for each shot. And then the results are then extracted into the form of a measurement count distribution. And finally, uh, here we plot a histogram of the distribution. And as you can see, we encounter a peak at our marked state of 101. So yeah, so basically like a common analogy of a use for the Grover algorithm would be like say you have 8 keys and one lock, and only one key can open the lock. So essentially, uh, instead of trying every key, all of the 8 keys to unlock the lock, uh, you're essentially using this algorithm to optimize your search for that one key that unlocks the lock. And here you can see the dashboard of the quantum platform of Qiskit. And uh, for this specific task, we use the IBM RISC-V backend, and only used 4 seconds of the quantum computer, and this was run on the open plan. So yeah, we as you can see, there's about 9 minutes and 45 seconds left of usage. So yeah, this was the presentation on Grover's algorithm.